Okay, so in the previous video, we had discussed this condition, that is, the load should be placed in the same ratio as it divides the span. In that case, you will get a maximum bending moment. Okay, at a section, at any section C. Now, with this, we have just one more thing to learn. That is, what is the position for absolute maximum moment. Okay. Now this position, as we have seen in earlier cases, here YC, the ordinate should be maximum for maximum, absolute maximum bending moment. So that YC, we already know what is the ordinate is Z into L minus Z by L. This is the maximum ordinate. So for YC to be maximum, you have to locate the position Z, which section. It's not that your section Z can vary from 0 to L. But our section everyone, so that you get maximum, absolute maximum moment. That is what you have to locate. So for YC to be maximum, dyc by dz with respect to dz should be equal to 0, isn't it? For yc to be maximum. Okay, when yc is maximum, you get multiplied by load, you get the absolute maximum moment. So differentiate this expression with respect to z, and what you get is L minus 2z equal to 0, or it means L is equal to 2z, or Z is equal to L by 2. So like we discussed in the earlier derivations, absolute maximum moment. Okay, therefore the result is absolute maximum moment occurs at midspan. Okay, occurs at midspan. The position of load is in such a way that the section divides the load in the same ratio as it divides the span, which means in order to get absolute maximum moment, the center of gravity of the load will be placed at midspan. That you have already discussed that x by d should be equal to z by l. But in this case, your z is equal to l by 2. So your x by d should also be having the same ratio 1 by 2, which means the load, if this is your load, exactly at the CG of load, that should fall on the midspan. At L by 2, you have to keep the, so if this is your AB span and this is L by 2, then your load should be placed in such a way that the CG of the load also coincides with the midspan. In that case, you get absolute maximum moment. Okay, so that also we can write the position of load, okay, is to be such that position of load is to be such that the section divides the load, the section divides the load in the same ratio, as it divides, the span, which means that the absolute maximum moment center of gravity of load should be at the midspan. Okay, so position of load is to be such that the section divides the load in the same ratio as it divides the span, which means that for absolute maximum moment, CG of load should be at the midspan. Okay, so that is also an important result for ILD for UDL smaller than span. Next, we are going to see a problem, and then we will move on to a train of concentrated loads. Okay, so so we'll move on to a problem. So in this, the question is this: a simply supported beam. I'll just Okay, so as you can see here, a simply supported beam has a span of 15 meters, UDL of 40 kilonewton per meter and 5 meter long, crosses the girder from left to right. You have to draw the ILD for shear force and bending moment at a section 6 meters from the left end. So this is 6 meters. And using these diagrams, you have to calculate the maximum shear force and bending moment at this section. Okay, so it is quite easy. You have been asked to draw the ILD first. So let us draw that first. And I'll just show the uh, load here as a separate thing in red. So this is UDL and its value is 40 kilonewton per meter, and it is 5 meters long. Okay. Okay. So this is your section 6 meters. The total span is 15 meters, which means BC is 9 meters. Okay, now the ILD for shear force is like this. Okay, these figures and shapes and the ordinates are very important. You have to remember that. Okay, this is minus and this is plus. And let us also draw the ILD for bending moment, because that is also asked. So you have a triangular distribution like this with a maximum ordinate of Z into L minus Z by L. Okay, this is A, C, B. A, C, and B. Okay, now we have drawn the influence line diagram. Now it's just not enough. So as solution, we have to now sit and find out what is the ordinates. So first thing is you have to find ILD ordinate to the just to the left of C. Okay, just to the left of C is nothing but minus Z by L, which is equal to Z is already given minus 6 divided by 15. Okay, so you will get minus 0.4. This we are finding out to make calculations quick and easy. So we will find out the ordinates first. The next one is ILD ordinate to the right of C. Okay, right of C is nothing but positive L minus Z by L. So L minus Z is nothing but 15 minus 6 by 15 or 9 by 15, which is giving me a value 0.6. Okay, now as the next solution at C, we have to find a negative shear force. So to find a maximum negative shear force at section C, what is the formula? You have to multiply. This is a UDL smaller than the span, isn't it? So you have to multiply by UDL into the area of the ILD. So how you have to position the ILD is like this. So you know that the ILD is, I mean, UDL is only 5 meters, whereas AC is 6 meters. So the head of the UDL should reach C and the rest of it behind C. So this is 5 meters means you have a 1 meter left out. So this is your ILD. So this is one ordinate and this is 1 meter and this is 5 meters. So you have to find out what is this ordinate because you have already found out what is Z by L. So this is 0.4. You have to find out what is this. Let us call it X. Okay. So I'm going to find out that. So I'll just write at C, the negative shear force is maximum. At C, negative shear force is maximum when the head of load, okay, when the head of load touches or just reaches C, okay. Okay, just take the layout blank. Okay, I hope you have the figure in your mind. So I'll just draw the ordinates along here. Okay, this was how we had written. We have a point 4 here. Okay, and we have to find x here. This is 1 meter and this is 5 meters. This was how it was. So from similar triangles, 1 by 6 should be equal to x divided by zero point 0.4, which gives x is equal to 0.0666. Okay, so therefore you have maximum negative shear force at C is equal to 40 is the UDL. 40 into, you have to take the area of this trapezoid. This area is what you have to take. So I will take 40 into half, not half, yeah, half sum of parallel sides, that is 0.0666 plus zero point 0.4 into this height, which is 5. So simplifying, you get 46.667 kilonewton. This is your maximum negative shear force at C. No need to substitute it as minus and everything, because you're already specifying here that it's a maximum negative shear force. So we'll also find, so can you tell me what is maximum positive shear force? For maximum positive shear force at C, the tail of the load, tail of UDL should reach C or just cross C. Okay. So the thing should be positioned, I mean the UDL should be positioned like this. Okay. And this is 5 meters. So this distance will be 9 minus 5, 4 meters. Okay. So 5 meters, 4 meters, you have to find what is this y, this ordinate y. This one you have to find out, because this you have already found out as 0.6. This is 0.6. So I'm referring to the same figure which I have shown above. So from similar triangles, I can write y divided by 0.6 is equal to 4 divided by 9. Okay. So from this, I'll get y as 0.2667. Okay. Therefore, maximum positive shear force at C is equal to 40 into 0.2667 plus 0.6 divided by 2 into the height, which is 5 of the load, which gives me 86.667 kilonewton. Okay, I hope it's clear.